So this is what we're starting off with. So we're going to sketch the graph, and I'd like us to write the domain and the range of the following three functions. Anyone want to tell me what we call this kind of a function? That's the shape. Yeah, the shape is a parabola. It's a parabolic shape. The type of polynomial that this is, though, starts with a Q. Quadratic. Yeah, this is a quadratic. Okay. What? Anyone remember what we would call this? Radical. Yeah, this is a radical function. And this is a tan function. You know what family this guy belongs to? That's very close. Sinusoidal is so a sinusoid is a shape that looks like that, right? So sinusoidal is some kind of variation of that. So maybe something like this, right? Or something like this. Uh, one of those words is correct. Yeah, this is a trigonometric function. So this is a trigonometric function. Yeah, so I've got a quadratic function, I have a radical function, and I have a trigonometric function. So I'm going to give you a minute to graph these. I don't require them to be like picture perfect. We're just sort of estimating. I would just like us to sort of jog our memories to get a basic shape down. But don't feel like you need to draw it to scale. That's not the purpose of this. Some of the graphs that we're going to do this year, I am going to want you to do it to scale. But this one in particular, I'm just looking for sort of an eyeball kind of a graph. All right. Okay. So let's think about this first one here. So this is the graph of f of x equals x squared. If you like, you could think of it as y equals x squared. That's typically how we graph things, is that y equals f of x. So let's try this one. So remember that a parabola shape is a shape that looks something like that, little smiley face. We could talk all day about parabolas. There's a lot to say about parabolas. But in general, this particular shape, like I'm not trying to go for too many details here, but we'll get a little bit of precision, just a tiny bit. So we start. Maybe I'll do a different color actually. So we start off at the origin 0, 0, and then we go over 1 and up 1, right? Because 1 squared is 1, right? And then if I go over 2, 1, 2, 2 squared is 4, so I go up 1, 2, 3, 4, and you can kind of see how it gets steeper and steeper as we go. And something that's really important, and something that I always try to emphasize with parabolas, students have a tendency to make parabolas look like this. And we are going to find this year that this is incredibly wrong for a very important reason. Parabolas are not pointy. They're absolutely not pointy. They have a round bottom. Okay, so it seems kind of like a silly thing to be concerned about, but in calculus in particular, we really want to know about functions that are pointy like this and functions that are smooth like that. So it sounds like kind of like I'm being finicky here, but it is really important that at this point right here, the function is actually flat. It's flat. And if you don't believe me, we could head over to Desmos and take a quick chat. My iPad is really jumpy today. It keeps hopping all over the place. Let's take a quick peek at the function y equals x squared. So if I just do x squared, see there it is. It's nice and flat on the bottom. And if you zoomed in really close, you'll see that it is actually flat at when x is equal to 0. So, like I said, it sounds like it's like, who cares? Pointy, flat, like not a big deal. It's just a picture. Turns out that pointy functions have something fundamentally different than smooth functions when we start looking at something called the derivative. Okay, let's think about g of x. So g of x is x squared. So does anyone want to sort of describe this one to me? Quadrant 1. And which one is quadrant 1 again? Okay, so it's only in quadrant 1, so the whole function takes place in this quadrant. Yeah. Okay. Can you tell me any important points? Yeah, steep. I would say steep because it's kind of like vertical. Mm-hmm. Mm-hmm. Does it share any sort of properties with a parabola? Because remember that an exponential would look like that, right? Reflected it on x equals where y equals x. Okay, so something like this. So take. I see. Okay, so here's the line y equals x. Y equals x. Okay, and then if we reflected this function along there like this, then that would be y equals square root of x. Okay, and that makes sense on an algebraic level too, right? Because these two things are opposites, right? Taking the square root of something or squaring something is the exact opposite. So in a lot of ways, if we said that like y is equal to the square root of x, it's a very similar thing to saying that y squared equals x, which is kind of like the opposite of this one, right? So the shape is very similar to a parabola, but since we all know that we can't take the square root of a negative number, there's nothing over here. And then also we don't have this portion of the parabola, and that's because this is a function, right? So each value of x only gets mapped to a single value of y. Okay. If we did have this, then all of a sudden this wouldn't be a function anymore. Okay. So a lot of people tend to think that something like the square root of 9 is equal to plus or minus 3. That is not true. The square root of 9 is equal just to 3. Just to 3. Okay? When you take the square root of a number, you're only taking the positive value. This is called the principal square root. Okay? So when you're taking the square root of something, you're only taking the positive value. So for that reason, we only have our function on one side of the x-axis. Okay, what about tan of x? I'm thinking that if we had trouble with any of these, tan of x is probably one of the more challenging ones. So let's go over tan of x. Tan of x. So by the way, I should be labeling these. This is y equals x squared. This is y equals the square root of x. Okay, let's think about tan of x. Okay, and let me make it some better lines here. Okay, let me just give me 2 seconds to make some nice straight lines. There we go. Okay. So, just for your benefit, since I kind of got the sense over the past a couple of weeks that trigonometry was a challenge last year, and that I think that maybe there were some sections that were omitted due to the pandemic, which is fine. Like that's not like you're not to blame for that. Your teacher's not to blame for that. We were in a pandemic. There were things in the curriculum last year that I didn't get to teach either, right? We were all doing our best. So, one of my goals for the beginning of the year is to kind of try to refresh your memory a little bit with trigonometry, and some of it might be new to you as well. So in part of that, I printed out a few little graphs. I know that they're really small. You might need like some binoculars if you're in the back of the class. But one of those graphs is the graph of tan of x. So you can use that as a little reference. there's a few things that I like to remember about tan of x. So tan of x is equal to sine of x over cos of x. Okay, so that's what tan of x means. And anytime you have a fraction, you do need to be concerned about when that fraction has a zero denominator, right? Because we can't have zero as a denominator. That is undefined, right? That's a huge topic in calculus, is thinking about what happens when you divide by zero. There's all sorts of things can happen when you divide by zero. So here we want to make sure that since if cos of x is equal to 0, then tan of x is undefined. I'll just write UND, undefined. Okay? So we need to find all the values that cosine of x is equal to 0. Okay, so let's draw a quick circle here. This is the model of trigonometry that we're going to be using the most, is the unit circle model. So thinking about the unit circle, so the unit circle is a nice way of thinking about trigonometry because it tells us exactly where these values come from. So anytime we take like the sine or the cosine of an angle, really what we're doing is we're looking at the x and y values on the unit circle. If this is our angle theta, okay. So x here is our cosine of theta, and our y value is our sine of theta. Okay. So we want to know when is cosine of theta equal to 0? Well, that would be when the x value here is 0. So that occurs when we have a vertical line here or a vertical line here, because that would give us an x coordinate of 0, right? So because these are the points, this is the point 0, 1, and this is the point 0, negative 1. So if we recall some of these values, this over here, 180 degrees is pi radians. We're going to be exclusively working in radians this year. This value right here, this 90 degrees, is pi over 2. And this over here is, thank you very much, 3 pi over 2. And this point over here, we can call it either 0 radians, or 2 pi radians. And of course, the thing is you can keep spinning around and around and around. It's cyclical, so all of these values will repeat themselves. So anytime we have an angle of 2 pi radians or 3 pi over 2 radians, we have a bit of a problem. Another thing we can think of too is going in the negative direction. So this is also, if we wanted to, we could think of this as negative pi over 2 radians. So let's think about the values that we're not allowed to be equal to, and take it from there. So if this is like 1, 2, 3, 4, 5, 6, 7, etc. So I'm not going to write all these little ticks, but it's a 1-to-1 scale. Then we want to make sure that at pi over 2 is the first place that we have an issue. So pi over 2, well pi is a little bit more than 3. So pi over 2 is a little bit more than 1.5. Okay, so let's call it like 1.6. So right around here, we have a vertical asymptote. Okay, so this means that in the function tan of x, x is not allowed to be equal to pi over 2. Okay. Similarly, on the negative side, we also have negative pi over 2. That gives us a problem. Okay, so we have a problem here. Here's negative pi over 2. And then any like if I add 2 pi radians, 2 pi radians is a full revolution. I'm going to wind up where I started again. So any of these values plus 2 pi radians gives me another problem. Okay, so we have So we've got a distance of pi radians between here and here. So every pi radians, we have an issue. So this is going to be 1.5 plus plus pi. So I guess what we can do, if you really want, you can use a calculator. So let's do like 3.14 plus 3.14 divided by 2. So that gives me, 4.9. So just past 5. So here's my next vertical asymptote is just by 5. And we're getting the same thing over and over again. So 1, 2, 3, 4, 5. Okay. So these are all our vertical asymptotes. So this function has a period. Okay, a period means there is a certain space that just keeps getting repeated and repeated and repeated. Okay. The function ends up looking something like this. So it does cross the origin. It approaches the asymptote increasing on the left-hand side of the asymptote, and it is decreasing going towards negative infinity on the right-hand side of the asymptote. And it looks something like this. Oops, kind of made that look not the nicest. Let's try that again. Okay, there you go. Okay, and it's going to do the same thing on each of these little periods. So it just keeps on going over and over and over again. Okay, and we won't concern ourselves too much with like how curvy it is. Like maybe your drawing looks a little bit more like this, and then maybe someone else's drawing looks more like this. I'm not too concerned about that shape right now. What I'm concerned about is that you know that there are these asymptotes that happen every pi radian, okay? And that the function repeats itself in this kind of a manner. And like I said before, there is a picture of tan of x just over there right by that little cork board. And there's some other functions as well. So if you would like me to try to print those out larger, and so we could have a few more posters, just as a quick reference, I can do that. Just let me know. But for now, I'm just going to leave those up so you can have that as a quick reference. Okay, so those are our 3 functions. We still would like to talk about the domain and range of these functions. So let's think about the domain and the range. So let's start off with this one here. Let's do domain and range. Anyone want to help me out finding the domain of this first one? Yeah, because you can square any number you want, right? Take any number, square it, no problems there, right? So the way we would express that is we would just write the set of real numbers. So this is the set of real numbers. Real numbers. The set of real numbers is pretty much every number that you can think of, except possibly for imaginary numbers. So an imaginary number is where you would include something like the square root of -1. So that's a set that we're not really going to look too much at this year. If you end up studying calculus, it ends up being a fairly important set of values, but we're not worried about those for now. We're just worried about real numbers. So that includes things like the square root of 2, right? It includes things like fractions and decimals and that kind of thing. It includes pi. So the domain is the real numbers. The range, so the range is all of the y values that we've used. Doesn't really look like there's much going on down here, right? So we can't actually get a negative number back if we square it, right? The square of any number, even a negative number, is going to give us something positive. So the way we're going to write that, well, there's several ways that we can write it. One way is using set notation. So I'll use a curly bracket to represent a set, and I will say that the range is all values. Actually, we should use y because we're talking about the range. So y in the set of real numbers, we want to first say, okay, we're dealing with real numbers. Okay, so the range is a real number. such that, so that means such that, so now we're clarifying a little bit more about our set. We're saying, okay, yeah, it's a real number, but we've got more to say. Y must be greater than or equal to 0. So that's one way you could say it. So this is using set notation. Okay. Another way to use it is using an interval, and the interval would be something like this. We would say that, well, the smallest value that we have is 0. Exactly. It means that we did include 0, just like how we have y is greater than or equal to, right? It includes 0 in the set. So that's what the square bracket is all about, that we are including 0, and then we're going all the way to positive infinity. But you can never include infinity in your set because infinity is not a real number. You can kind of think of infinity as like a direction, right? Like north, right? So like if you that's kind of how I think of it. It's kind of like the direction north. Like you can walk in the direction of north, but you can't be on north, right? You can't be, it's not a location, it's a direction. So just like in that infinity is a direction. So we're not including it in our set, but we are saying that that's where we're going. We go all the way to infinity. So that's our range. Okay, what about this next one? Let's worry about our domain and range here. So domain and range. So do we have any negatives in our domain? No. Did we include 0? Is 0 a member of our domain? Yeah. You can take the square root of 0. Square root of 0, that's equal to 0. No problem. So the domain here, I'm going to start at 0, and then there's no limit, so I just go all the way to infinity, and then the range is the same thing. Go from 0 to positive infinity. Okay, and if you wanted to, you could use that set notation as well. Whatever you prefer. Whatever you prefer. Okay, and finally, let's take a look at this one. So this is going to be an interesting one. So let's take a look at, well, first of all, let's start off with the range. Let's start off with the range. The range is going to be fairly straightforward, okay? The range just includes everything, right? Like this keeps on going up and up and up and up. There's no limit to how high it goes, and there's no limit to how low it goes. So the range here is the real numbers, okay? So that part is straightforward enough, right? It keeps on going. That's what these arrows indicate, right? This arrow indicates that we're going up forever, right? There's no limit to the highest point. The domain, however, the domain is a little more complicated. So we're allowed to take any real number except certain values. So we are allowed to take any of these numbers, but not this one, not this one, not this one, not that one. Okay, so we need to come up with a way using algebra to describe all of those numbers. Okay, and I'll show you kind of the standard way of doing that. I wonder if you've seen this before. So when I show you this to you, I'd like just with a show of hands, if you could tell me if you've done this kind of thing before. And if you haven't, that's okay. I just want to know so that I know how much I should be teaching you, or if there's any things I can just expect that we all know. So the way we would say this is we would say, okay, well, my domain, I'm dealing with real numbers. Okay, that's pretty much how all of our domains should start, right? Saying that, okay, it's a real number. But now we have to clarify what kind of real numbers we're talking about. So x is a real number such that, by the way, some people do the such that with a bar like that. You can do whatever you like. I prefer the colon. I don't know why. I just always have used the colon. So x is a real number such that, well, instead of saying what x can be, let's talk about what x cannot be, okay? So because it's basically all of it except for particular values. So we're going to specify which values we're not allowed to be equal to. So I'm going to say that x cannot be equal to, well, let's start off with this one, pi over 2, right? That's the first value that we have. X cannot be equal to pi over 2, okay? But it's not just that, value, right? It's not just pi over 2, right? It's this one and this one and this one, and there's infinitely many ones that we didn't even write down, right? If you look at this graph, let's take a quick gander at Desmos. Let's take a look at tan of x. Okay, I guess they don't actually do the asymptotes for this, but you can see it just keeps on going on and on and on and on forever, right? Like I said, it has a period of pi, right? So every pi radians, we get the same thing. We get the same thing all over again. So because we know what the period is, we can say that every pi radians, we get another asymptote. So what I'm going to say is I'm going to say plus k times pi. Okay, so basically that's saying take pi over 2 and multiply and add some multiple of pi. But now I have to say, by the way, k is an integer. Okay, so integer is a capital Z. Okay, so integers are numbers like 1, 2, 3, 0, -1, -2. Okay, so that's what an integer is. Okay, so an integer is basically like a whole number that's maybe negative or 0. Okay, so I'm taking an integer multiple of pi. So take pi, multiply it by any integer, like multiply it by 7, add pi over 2, and there we have an asymptote. Okay, so this is the domain. Okay, so just a show of hands, can you tell me, have you done something like that before, where you've looked at an integer multiple of pi? No? Okay, so we should work on that, because that sort of thing is going to come up in calculus. So I'll do a quick survey of the other clusters as well. I think you're all pretty much in the same boat. So if this doesn't make perfect sense, like, don't sweat it. You've had, like, what is that, 4 minutes of instruction on this. This sort of thing gets easier the more you do it. But this is how we would describe the domain of tan of x. Okay. Any questions so far? No. Okay. So I anticipate like a little bit of work that we're gonna have to do with this sort of thing. But I think we'll be okay. I think we'll be okay. Okay, so what I'd like you to do is, with a partner, I'd like you to spend, we'll do 1 minute. I want you to explain how to find the domain of a function. Okay, so you've got 1 minute starting now. So I guess we've only got 2 sets of partners. This physically probably looks like, you probably know who your partner should be. But yeah, I want you to talk a little bit about how you would go about finding the domain. Okay, go. Okay, that's been 1 minute. Awesome. Okay, sorry if you're watching this video. The microphone probably sounds terrible, but maybe that's better. Okay. Yeah, we let's talk a little bit about some of the things we came up with. So at the back, would you guys like to start off? Like, were there any sort of things that you would start off with if you wanted to find the domain of a function? So look at values of x. So that would be like on the graph. Yeah, on the graph. Okay, so that's how you do it visually. Okay, did you think of a way of maybe doing it with algebra? Like if you didn't have the graph? No? Okay, okay. So but this is really good because we're going to be doing a lot of this just looking at a graph and seeing what the domain is just by observing it. So yeah, you're looking at the values of x, right? You don't really care how high you're going, right? All you really care about is which values of x you have been used. What about this other group? Okay, hold on. You're going faster than I can write. So we're going to look at the equation, and then ask, are there any rules being broken? Yeah. So what kind of rules are we talking about? Okay, so we got division by zero. Okay, so negative square roots. Okay, anything else? Here's one that people often don't know about, but 0 to the power of 0 is undefined. Okay, because on the one hand, 0 to the power of anything is 0, right? On the other hand, anything to the power of 0 is 1. So what is it? 0 or 1, right? So that's another one. There's a few more. And it's this in particular that calculus is really concerned about. That's what our focus is on. Is what happens when we break these rules? Like what's really going on behind the scenes? Like for so many years when you learn pre-calculus, it's like, oh yeah, no, you're dividing by 0, so who cares? It's just you're not allowed to do it. Calculus looks at those situations and says, okay, well, what is actually happening? Like what would happen if we allowed division by 0? What then? What sorts of equations would we get? That's what calculus is all about. Okay. All right. Now, again, with a partner, I want you to take a look at this graph. I'm going to give you 1 minute, and I want you to describe that graph. Like if you were to like maybe call someone on the phone and you didn't have any kind of piece of paper or anything, and you just verbally you wanted to describe this graph, how would you describe this graph with words? So you can go now. You've got 1 minute. Okay, that's been 1 minute. Do we want to start off at the back again? How would you describe this function? So we got y equals x. So remember y equals x, that would mean that our slope would be positive, right? This has negative slope, right? So it's very close to being y equals x. Do you want to correct it? Negative x, yeah. This y equals negative x, yeah. So from here to here, we've got y equals negative x. What's going on over here? Looks kind of exponential, yeah. Okay. Let's see if we can figure out what this function is. So if I go over 1, then I go up 1. Okay. If I go over 2, I go up 1, 2, 3, 4. Okay. If I go over 3, 1, 2, 3, I go up 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So what is it? What does this function kind of act like? Is it an exponential function? I think this is a quadratic. Yeah, this would be y equals x squared. So this is kind of like two functions in one, right? Kind of like we've taken these two functions, we've glued them together. So we've got two sort of different sections, right? We've got sort of a negative section. So this is where x is less than or equal to 0. And this is where x is greater than or equal to 0. So do you guys have anything to add to this?
I threw in the restrictions.
The restrictions, okay.
I got to do things. So I said y is equal to negative x, whereas if you're negative infinity, or equal to okay, less than equal to 0, and then x squared where in 0 and
Yeah. So this is yeah. Some people like to call this a piecewise defined function. So this is a piecewise function. Okay, and the way we would write this piecewise function is in the following way. We would say that f of x is equal to, well, it's equal to two things. So we use these nice little curly brackets, and then we write it in two rows, okay, one on top of the other. Typically, we start the first row with whatever is coming in on the left. So this function here. So we write f of x is equal to negative x. That's what this one is here, negative x. And then we write its domain. So we would say when x is less than or equal to 0. Okay? So that's the first portion. Okay? Then we write the next portion, which would be x squared when x is greater than 0. Okay? Now, it just so happened that these two functions kind of overlap at a single point, right? They both touch the origin. They both are on the point 0, 0. So in this case, it didn't actually really matter if we had the less than or equal to sign here or on the second one. It means the same thing. There may be some situations, like maybe if we had a different function like this, like maybe we had this function, right, that goes here, and then this function over here, then we would have to specify, okay, what happens at 0? Are we including this function or are we including this function? So we have to be a little bit careful about that. Okay, couple more things here. I think this is the last portion. Okay, maybe we'll leave this for tomorrow. You know what? Why don't we actually leave this portion for tomorrow? Okay, so you guys can watch the video, and then if you're, I guess, cluster, would that be C? If you're cluster C, then we'll do this in class together tomorrow. So yeah, let's leave it there. I've got a few more questions for you to work on, and they are at the bottom of this document. So if you haven't finished the first one from yesterday, that's what I would recommend you work on now. It's on Google Classroom, yeah, and I'm going to post this on Google Classroom in just a moment. Okay. So yeah, we'll leave it there. If you've made it through this video, then this is what I would recommend you work on. Questions 31 to 44. I'm going to end the video here. Bye-bye. Okay.